Hello everyone. Tarek already introduced Chili Chips team and Uber Code project. This was the first task and for us beginners. We did after Blinky we did implementing ADDA conversion on Arctic 7 FPGA with some practical approach. This is table overview of what we'll cover. Tarek already explained some hardware setup which we use. The core of the system is Alink 7 FPGA development board, which operates at a clock frequency of 200 megahertz, and we use these 12-bit dual AD converter, which has 65 million samples per second, and 14-bit dual DA converter, which has 125 million samples per second. And this difference in sampling rate will have some distortion in signals because of this. First one was DA conversion. We used official Alink's tutorial docs on site, and there you have much detailed description. We used a dual channel sine wave generation routine, so there's not much to say about it. We stored samples of sine wave in ROM memory. Then FPGA would read it and give it to the DA, which would generate analog signals. There was one variable which we incremented to change the frequency. It's basically it changes the speed that we go through these samples. So this is the lowest achievable frequency, 122 kilohertz, the highest achievable 15 megahertz, and the target for this project was 10 megahertz. And yes, we did it successfully. So now, colleague Nikola.
Similarly to the DA conversion, we also found a tutorial, official Alink's tutorial for the AD converter. Our task was to send a generated sine signal to the AD converter, sample it, and then display it via VGA. We send it via VGA from the FPGA board onto a display or a screen, just to see if the sampling was done correctly, and we got a correct sine wave on the screen, and we can say with confidence that we managed to sample it correctly. After that came the ADDA conversion. We used the knowledge we gained through those two tutorials to interface both AD and DA conversion. Just like the AD converter, we sent a signal starting from 1 megahertz and then incrementally stepping it up to 10 megahertz, which was our target for the project. You can see the picture of 1 megahertz on top, the 10 megahertz sine wave is on the bottom. What I would like to point out is that we got a lot of noise as we progressed through the frequencies up to 10 megahertz. We think that was probably because the AD converter has a 60 megahertz sampling rate, and the DA converter pushes up to 125 megahertz sampling rate. Next, please. We also tried to use send a square wave, square signal to the FPGA. You can see the 1 megahertz square on top and the 10 megahertz square, and as you can see, the 10 megahertz square does not look like a square at all. This was actually very useful to us, since now we know what we're dealing with and what we can actually use or not to use in the project. It was actually, the signals were a lot noisy, especially since it was a video. We cherry-picked a couple of signals so that they could look pretty for the presentations, but it was actually very noisy and it was very hard to pick out a good representative signal for this. And that's it for the ADDA converters.
Super.